Okay, let's talk about intermolecular forces. First of all, you have ionic and covalent. Okay, two things that we've talked about before. But as far as how they look, ionic bonds are going to form a highly organized crystal lattice. All that means is that it's uh, well, a lattice is just the structure of it due to very strong bonds. Okay, so if you were to draw a crystal lattice, if you're taking like sodium chloride, so you have your Na plus, which is very small, and you take your Cl minus, which is very large. Okay, what they're going to do, because the sodium is positive and the chlorine is negative, you're going to get these structure that looks like something like this. And if you can imagine this in 3 dimensions, continuing on like that, so it's obviously going to be very strong. Okay, let's move covalent down a little bit. Covalent bonds are similar. They're similar. They form crystal lattices as well in the solid form. Solids form a crystal lattice, but it's just not as strong. As strong. Okay, so they're forces, they're intermolecular forces, they're forces that hold molecules together, are not as strong. Okay. If we talk about covalent bonds a little bit more, these have bonds between atoms. And the bonds between the atoms are strong, so they hold together well, okay, but the attractive forces that hold other molecules together are weak. So the bonds between the atoms are strong. The attractive forces molecules are weak. So if you think of it like, I don't know, like just a chain of people, okay? So if you look at a chain of people, the bonds between the atoms, so the bonds that make the people stay together amongst themselves, that keep this guy's arms together. Okay, so the forces that keep the people together, that keep their heads on and their arms on and their legs together, and their body just together, are very strong. But the forces between them, when they hold their hands, that's weak, so they can be pulled apart. All right, so the people as a group can be pulled apart, but the people as individuals, they're stuck together. Okay, so if that makes sense to you, good. All right, so you have three types of forces. So nonpolar intermolecular forces. These are dispersion forces. Okay. In a polar bond, the polar intermolecular forces are dipole-dipole forces. And then the third one is hydrogen bonds. Okay, you don't really have to know anything except for, you know, when you have a nonpolar molecule, they're going to be held together by dispersion forces. Polar molecules are going to be held together by dipole-dipole forces, and then just what a hydrogen bond is. So a hydrogen bond, the hydrogen end of one dipole bonds to a fluorine, oxygen, or nitrogen on another dipole. Okay, so what do we mean by a dipole? If you were to look at water, okay, if you were to look at water, that, okay, but if you were to draw it as a Bohr model or as the atoms, you have something that looks like this. So you have your hydrogens here, and you have your oxygen up here. Okay. If we were to draw the electrons on there, okay, these are going to be sharing electrons. So oxygen has 2 there, okay, in the first energy level. Then it has 2 sets of paired electrons, right? And then these down here are the ones that it's sharing with hydrogen. So hydrogen's going to contribute 1, and oxygen's going to contribute 1, and they're going to share here to get this bond, okay? And again, they're going to share here to get that bond. All right. So basically, what happens is all of your negative stuff, or the majority of your negative stuff, is from this line and up. Okay. You have more negatives up here than you have positives. So this is going to be our slightly negative end. Okay, and that's not an 8. That's slightly. So it's slightly negative. Now down here, all we have are the 2 positive nuclei from hydrogen. There's no electrons down here that are negative to kind of balance out those positives. So this end down here is going to be slightly positive. Okay, so it creates one end, kind of like a magnet. You have one end that's slightly negative and one end that's slightly positive. Okay, so when you get those together, when you get multiple hydrogens, or sorry, multiple waters together, you're going to get, you know, a bond, a hydrogen bond. Let's say it goes this way, like that. Okay, because this end is slightly negative and this end is slightly positive. So they're just going to attract one another. Okay, that's why water sticks together so well. Okay, so, but it doesn't have to be a hydrogen to an oxygen. It could be a fluorine or it could be a nitrogen. It doesn't really matter, but that's how hydrogen bonds work. And this right here is what we mean by a dipole. Okay, where it has 2 poles. All right, a positive pole here and a negative pole there. Okay. Let's go over the properties of ionic and covalent compounds. Okay, you can just make a whole table here. Okay, you've got melting point, you've got phase at room temperature. Okay, so that's your state of matter. You've got hardness. Okay, how hard is it? You have solubility. You know, is it soluble in water? And finally, you have conductivity. Okay, so if we go back up, we're talking about ionic compounds first. Okay, Ionic compounds are going to have a relatively high boiling point and melting point. So the things that when you try to melt them, it takes a long time to do so, or it doesn't actually melt because you can't get it hot enough, those are going to be normally ionic compounds. As far as your phase at room temperature, most are solids. Hardness, these are very rigid and brittle. Okay, and then solubility, many are soluble in water. Not in a non-polar liquid. Okay, so if you try to put an ionic compound in a liquid that's not polar, like an acetone, it's not going to dissolve, okay, because it just doesn't have those properties. Finally, conductivity. These are poor conductors. Solids. Great conductors in the liquid state and in solution. Great conductors in solution. So when you mix them with water and in the liquid state. Okay. So that's ionic compounds. Those are the properties. So let's talk about covalent. All right, and if you can imagine, they're obviously different types of bonds, so they're going to have different properties, probably opposite. So covalent compounds or covalent molecules, they're bonds. They have low melting points. Okay, if you go back to the this right here, bonds between atoms are strong, but the attractive forces between the molecules are weak. That's why they're easy to be broken apart. That's why they're easily made into liquids. Okay. Most are gases at room temperature. If it happens to be in its solid state. Okay. Solubility. We're going to go with the like dissolves like. Meaning, if it's a polar molecule, it's going to dissolve in polar things. If it's a nonpolar molecule, it's going to dissolve in nonpolar things. All right, nonpolar liquids. And then conductivity. So polar molecules are good. Nonpolar molecules are poor conductors. Okay, so with conductivity, you have kind of two scenarios. With the ionic compounds, it's, well, is it a solid or is it a liquid, or is it in solution? And then that kind of determines its conductivity. With covalent molecules, it's more dependent on, is it polar or nonpolar. If it's polar, like water, it's going to conduct electricity. Okay, we know that. If it's nonpolar, it's not really going to conduct electricity because it doesn't have those dipoles to transfer the electrons on through. Okay, so that is properties of ionic and covalent compounds as well as intermolecular forces.